Imagine you are looking at the center of an atom. Hidden inside that tiny central region is the nucleus, which contains two types of particles, protons and neutrons. Among these particles, the proton plays the most important role in determining the identity of an element. The number of protons present in the nucleus is called the atomic number, and it is represented by the symbol Z. This is one of the most fundamental concepts in chemistry, because every element in the universe is identified by its atomic number. No matter where an atom is found on Earth, on another planet, or in a distant galaxy, if it has the same number of protons, it is the same element. Therefore, the atomic number acts like a permanent identity card or fingerprint of an element that never changes unless the atom undergoes a nuclear reaction. To understand atomic number more clearly, first remember that an atom consists of three subatomic particles. Protons have a positive electrical charge and are located inside the nucleus. Neutrons have no electrical charge and are also found inside the nucleus. Electrons carry a negative electrical charge and move around the nucleus in different energy levels or electron shells. Although electrons and neutrons are important for the atom's properties and behavior, neither of them determines which element an atom is. Only the number of protons decides the identity of an element. This is why the atomic number is always defined as the number of protons present in the nucleus. For example, if an atom contains only one proton, it is always hydrogen. If an atom has 6 protons, it is carbon. If it contains 8 protons, it is oxygen. If it has 79 protons, it is gold. These numbers never change for their respective elements. An atom with 8 protons can never become carbon because carbon must always have 6 protons. Similarly, an atom with 79 protons will always be gold. This simple rule allows scientists to identify every known element in the periodic table. The atomic number is represented by the letter Z, which comes from the German word Zahl, meaning number. Whenever you see the symbol Z in chemistry, it refers specifically to the number of protons inside the nucleus. Chemists use this symbol in chemical equations, atomic notation, and scientific calculations because it provides an easy way to identify elements without writing their full names every time. One of the most important facts about atomic number is that it tells us the number of electrons in a neutral atom. A neutral atom has no overall electrical charge because the number of positive protons equals the number of negative electrons. Since each proton has a charge of +1 and each electron has a charge of 1, these charges cancel each other out. Therefore, if an oxygen atom has 8 protons, it must also have 8 electrons to remain electrically neutral. Likewise, a carbon atom with 6 protons has 6 electrons, and a hydrogen atom with 1 proton has 1 electron. However, if an atom gains or loses electrons, it becomes an ion, but its atomic number does not change. For example, a sodium atom normally has 11 protons and 11 electrons. If it loses 1 electron, it becomes a positively charged sodium ion with 11 protons and 10 electrons. Even though the number of electrons has changed, the atomic number remains 11 because the number of protons is still the same. This shows that atomic number depends only on protons, not on electrons or neutrons. The atomic number is also used to arrange elements in the modern periodic table. The periodic table is organized in increasing order of atomic number, not atomic mass. Hydrogen is placed first because it has 1 proton. Helium comes next with 2 protons. Lithium has 3 protons. Beryllium has 4. Boron has 5. Carbon has 6. Nitrogen has 7. Oxygen has 8. And the sequence continues until the heaviest known elements. This arrangement allows scientists to observe repeating patterns in chemical properties and predict the behavior of different elements. Another important point is that the atomic number determines the electron configuration of an atom. Since the number of electrons in a neutral atom equals the atomic number, Scientists can calculate how electrons are distributed in different energy levels. This electron arrangement controls how atoms react with one another, how they form chemical bonds, and what compounds they can produce. In other words, the atomic number indirectly determines the chemical behavior of an element, because it decides the electron arrangement. It is also important not to confuse atomic number with mass number. The atomic number counts only protons, whereas the mass number counts both protons and neutrons. For example, the most common oxygen atom has 8 protons and 8 neutrons. Its atomic number is 8 because there are 8 protons, while its mass number is 16 because 8 protons plus 8 neutrons equals 16. Even if the number of neutrons changes, the atomic number remains the same because the number of protons has not changed. This leads us to the concept of isotopes. Isotopes are atoms of the same element that have the same number of protons but different numbers of neutrons. For example, carbon-12, carbon-13, and carbon-14 are all isotopes of carbon. Each one contains exactly 6 protons, so each has an atomic number of 6. However, they contain different numbers of neutrons, which gives them different mass numbers. Even though their masses are different, they all remain carbon because their atomic number has not changed. Let us take the example of oxygen shown in the illustration. Oxygen has an atomic number of 8, which means every oxygen atom contains 8 protons inside its nucleus. In a neutral oxygen atom, there are also 8 electrons surrounding the nucleus. Usually, 2 electrons occupy the first energy level, while the remaining 6 occupy the second energy level. This electron arrangement explains why oxygen easily forms chemical bonds with other elements, especially hydrogen, to produce water. The process of identifying an element using atomic number is very simple. First, count the number of protons in the nucleus. Second, that number is the atomic number, represented by Z. Third, locate that atomic number on the periodic table. The element corresponding to that number is the identity of the atom. For instance, if you count 8 protons, the atomic number is 8 and the element is oxygen. If you count 6 protons, the atomic number is 6 and the element is carbon. This method works for every element known to science. Scientists rely on atomic number in many fields of science and technology. In medicine, radioactive isotopes are identified by their atomic numbers. In biology, the atomic numbers of carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur help explain the composition of living organisms. In environmental science, atomic numbers help identify pollutants and trace elements. In astronomy, scientists determine the elements present in stars by analyzing their atomic numbers through spectroscopy. In nuclear chemistry, atomic number is essential for understanding radioactive decay and nuclear reactions. A simple way to remember this concept is to think of the atomic number as the permanent ID number of an element. Just as every person has a unique identification number, every element has a unique atomic number. Hydrogen will always be number 1, carbon will always be number 6, oxygen will always be number 8, and gold will always be number 79. The number of electrons or neutrons may change under certain conditions, but the number of protons remains the defining feature of the element. So, whenever you see the term atomic number, immediately remember one simple definition. Atomic number squark, number of protons in the nucleus. This single concept is the foundation of atomic structure, the organization of the periodic table, electron arrangement, chemical properties, and the identification of every element in the universe. Once you fully understand the atomic number, learning the rest of chemistry becomes much easier because it serves as the starting point for understanding atoms, elements, ions, isotopes, and chemical reactions. The next important concept after atomic number is the mass number, represented by the symbol A. While the atomic number tells us only the number of protons in an atom, the mass number tells us the total number of particles present inside the nucleus. These particles are called nucleons, and they include both protons and neutrons. Since almost all of an atom's mass is concentrated in the nucleus, scientists use the total number of protons and neutrons to determine the mass number. Therefore, the mass number is defined as the total number of protons and neutrons present in the nucleus of an atom. In simple words, if you count all the protons and then count all the neutrons and add them together, the result is the mass number. The mass number is represented by the capital letter A. The mathematical formula is very simple. Mass number secus, number of protons plus number of neutrons. This formula is often written as AWP plus N, where P represents the number of protons and N represents the number of neutrons. It is one of the most frequently used formulas in atomic structure because it allows scientists to calculate the total number of particles inside the nucleus. To understand this better, remember that the nucleus contains only protons and neutrons. Electrons are located outside the nucleus in different energy levels or shells. Since electrons have an extremely small mass, about 1/1836, the mass of a proton, their contribution to the total mass of an atom, is almost negligible. For this reason, electrons are not included when calculating the mass number. The mass number depends only on the particles present inside the nucleus. For example, consider the carbon atom shown in the illustration. Carbon contains 6 protons and 6 neutrons in its nucleus. Using the formula AWP plus N, we simply add these numbers together. 6 protons plus 6 neutrons equals 12. Therefore, the mass number of this carbon atom is 12. This is why the atom is called carbon-12. The number after the element's name always represents its mass number. Let's look at another example. Suppose an atom contains 8 protons and 8 neutrons. Adding these together gives 16. Therefore, its mass number is 16, and if the atom has 8 protons, it is oxygen. This atom is called oxygen-16. Similarly, sodium contains 11 protons and 12 neutrons, so its mass number is 23. Chlorine has 17 protons and 18 neutrons, giving it a mass number of 35. In every case, the calculation is the same, simply add the number of protons and neutrons. One important point students must understand is that mass number is always a whole number. Since protons and neutrons are whole particles, you cannot have half a proton or half a neutron inside a normal atom. Therefore, the mass number is always an integer such as 12, 16, 23, or 35. It is never written as a decimal. This makes it different from the atomic mass shown in the periodic table, which is often a decimal, because it represents the weighted average mass of all naturally occurring isotopes of an element. The mass number should never be confused with the atomic number. These two quantities are related but completely different. The atomic number counts only the protons, while the mass number counts both protons and neutrons. For example, carbon has an atomic number of 6, meaning it has 6 protons. Its most common isotope has a mass number of 12, meaning it has 6 protons plus 6 neutrons. Oxygen has an atomic number of 8, but a common mass number of 16, meaning 8 protons and 8 neutrons. So, the atomic number identifies the element, while the mass number tells us how many particles are present in its nucleus. Another very useful relationship comes from rearranging the mass number formula. Since mass number scarc protons plus neutrons, we can also calculate the number of neutrons if we already know the mass number and atomic number. The formula becomes number of neutrons tex, mass number atomic number, or NAAZ. Here, A represents the mass number and Z represents the atomic number. This formula is extremely important because examination questions often ask students to calculate the number of neutrons using these values. For example, suppose an oxygen atom has a mass number of 16 and an atomic number of 8. The number of neutrons is calculated as 16 8 8. Therefore, oxygen has 8 neutrons. Similarly, sodium has a mass number of 23 and an atomic number of 11. The number of neutrons is 2311 Doke 12. Chlorine 35 has an atomic number of 17, so the number of neutrons is 3517 Doke 18. These simple calculations are commonly used in chemistry. One of the most interesting applications of mass number is in understanding isotopes. Isotopes are atoms of the same element that have the same number of protons but different numbers of neutrons. Because the number of protons remains constant, the atomic number remains the same. However, changing the number of neutrons changes the mass number. This is why different isotopes of the same element have different mass numbers. The illustration shows 3 isotopes of carbon: carbon-12, carbon-13, and carbon-14. All 3 atoms contain 6 protons, so they all have the same atomic number of 6 and are all carbon atoms. However, carbon-12 contains 6 neutrons, giving it a mass number of 12. Carbon-13 contains 7 neutrons, giving it a mass number of 13. Carbon-14 contains 8 neutrons, giving it a mass number of 14. Although their masses are different, they all remain carbon because the number of protons has not changed. This example demonstrates an important scientific principle. Changing the number of neutrons changes the mass number but does not change the identity of the element. On the other hand, changing the number of protons changes the atomic number and creates a completely different element. Therefore, protons determine the identity of an element, while neutrons mainly affect its mass and nuclear stability. Mass number also plays a significant role in nuclear science. Scientists use it to identify isotopes, study radioactive decay, calculate nuclear reactions, and understand nuclear energy. In medicine, radioactive isotopes such as carbon-14, iodine-131, and technetium-99 are identified by their mass numbers and are widely used in diagnosis and treatment. In archaeology, carbon-14 dating helps scientists determine the age of ancient fossils and archaeological artifacts. In biology, isotopes are used to trace chemical processes inside living organisms. Thus, the concept of mass number is not only important in chemistry but also in medicine, physics, biology, environmental science, and many other scientific fields. Whenever you solve chemistry problems involving mass number, follow these simple steps. First, identify the number of protons. Second, identify the number of neutrons. Third, add them together using the formula AWP plus N. If you are instead asked to find the number of neutrons, subtract the atomic number from the mass number using NDO-AZ. These 2 formulas are the foundation of many numerical problems in atomic structure. A simple way to remember this concept is to think of the nucleus as a container filled with 2 types of particles: protons and neutrons. If you count only the protons, you obtain the atomic number, which identifies the element. If you count both the protons and neutrons together, you obtain the mass number, which represents the total number of nucleons in the nucleus. This distinction is one of the most important ideas in atomic structure and forms the basis for understanding isotopes, nuclear reactions, and many advanced topics in chemistry.